An important thing to understand when using the equation work equals force times distance is that this force is really an average force, because only in an ideal situation is there a constant force applied, and we kind of have been thinking about these forces applied as being constant. And when it is constant, the constant force is the average force, and you can just plug in that number for force. But most situations aren't that ideal, and the force does change, so we have to be conscious about using the average force instead of just some value for force. The contraction of a spring is an example where the force certainly is not constant. The more you compress the spring, the more force you have to apply to keep it compressed. The graph on the slide here represents the force it takes to compress a spring. When it's at equilibrium position, it takes basically no force to shift it from equilibrium. But the farther it gets from equilibrium, the more force it takes. And this last point is just going to be the final compression position. And this amount of force it takes to compress it to the maximum final X position, XF, let's just call this F. So it takes F amount of force to compress the spring to the XF position. And if we want to find the work that it took to compress the spring that far, and by the way, the work that we put into the spring equals the potential energy that the spring holds, we would have to figure out the average force times that distance. And since the force goes up in a straight line, we can see that halfway up we have the average force. So that the average force over the course of this entire compression of the spring is half of the maximum force. And that bar above here means average. So we can go ahead and put in for our average force half of the F max, and the distance overall that it was compressed was the XF. So the force we can describe, that maximum force F here, we can describe it in terms of the force constant of the spring. Because at the maximum displacement, that force required is the spring constant times that displacement. So if we put in KXF instead of F here, we get half times K times X, which is half kx squared, and that is the equation you can use for the potential energy held in a spring. But there's also another way we could come to that equation, and it's important to be able to understand how to do that, because you should understand that here's an instance where the work done to move the spring, and therefore the potential energy held in the spring, is equal to the area under the graph of force versus distance. So we could say that the work is the potential energy, the work done on the spring is the potential energy that is then held in the spring, which is the area under this graph. So all we have to do is find the area of this triangle, which shouldn't be too hard. We know this side has a length of F, that force it takes to maximally displace the spring. And then this side is XF, that maximum value of the displacement. And the area of a right triangle is half times one side times the other. And again, we know that force to compress it all the way is equal to the spring constant times the displacement. and then we already had that other XF in there, so again, we can come to the same conclusion about the potential energy held in the spring, but in a different way.